Hello, this is Karthik. I'm going to start my presentation by explaining the basics of evolutionary algorithm and some history about evolutionary algorithm and how it works, mm, and some applications of evolutionary algorithms. Next, we're going to move forward talking about genetic programming, some applications about genetic programming, and why we are using genetic programming in our case. The rest of the part, that is the next 50%, how the genetic programming parameters are set up over in our case, and the performance of the fitness function, the data preprocessing, and the results will be explained by Ananya. Let's start. Evolutionary algorithm is a subset of evolutionary computation that are designed to address optimization and search problems by replicating the natural evolution process. Evolutionary algorithms are inspired by Darwin evolutions. EAs are based on the principle of natural selection and genetics, where the fittest individuals are more likely to survive and reproduce. They are basically population-based methods. They work with a population of candidate solutions, evolving this population over time, and going to pick the best fittest individual among them. The uses of genetic operators. Key operation includes selection, crossover, and mutation. Comparing to other algorithms, evolutionary algorithm uses the same template, selection, crossover, and mutation, to every algorithms out there, like genetic programming, grammatical evolution, and even GAs. The templates are going to remain same, selection, crossover, and mutation. We're just going to change the parameters and change some fitness functions to get the best individual among them. The main types of evolutionary algorithms are genetic algorithms, evolutionary strategies, genetic programming, and differential evaluation. GAS uses binary strings to represent solutions, that is, zeros and ones in an array format. Employing crossover and mutation to evolve these strings. Evaluation strategies. They basically focus on optimizing real valued parameters, often used for continuous optimization problems. Genetic programming, where we used in our problem. GP basically uses tree-like structure to represent computer programs or mathematical expression. Then finally, differential evaluation involves differential mutation and crossover, typically used for multidimensional real-valued functions. Evolutionary algorithm contains 6 steps: initialization, evaluation, selection, crossover, mutation, and replacement. Initialization starts with a randomly generated population of individuals or potential solutions and moves to evaluation, where accessing each individual using a fitness function, whether they are fitter to solve this problem or not. And then it moves to selection. This is the process of choosing which solutions or chromosomes will be kept for the next generation. The selection is often based on the fitness of the solutions. The ones that perform better have a higher chance of being selected. This mimics natural selection, where fitter individuals are more likely to survive and reproduce. And then we move to crossover, also known as recombination. This is the process combines the genetic information of two parents solution to produce one or more offspring solutions. It's a way of mixing genetic information of parents to potentially produce fitter offsprings. There are various methods of crossover, such as single point, 2-point, and uniform crossover. And then we move to mutation. This introduces variation into the population of solution. It randomly alters one or more gene value in the chromosomes to create a new solution. Mutation ensures genetic diversity within the population, helping to prevent premature convergence on poor solutions. Replacement. From a new generation of the population, often by replacing the less fit individuals. The major applications of EAs are optimizing problems, where GAs and GPs are exceptionally good in solving a problem, like scheduling, resource allocation, and route planning. They also use in machine learning field like feature selection, hyperparameter optimization. They also use this in control systems, developing strategies for autonomous systems, and combining EAs with other techniques like neural networks and adaptive algorithms. Algorithms adjust their parameters dynamically. Scalability improvements, enhancing EAs to handle larger and more complex problems. Our problem statement is simple: to predict whether the person's income exceeds $50,000 per annum based on census data. The dataset contains features like age, capital gain, and so on. Using these input features, we should predict whether the person's income surpassed $50,000 or not. That's it. We are using genetic programming to solve this problem. You can see the background contains a tree, which indicates that genetic programming uses a tree-like structure to solve a problem. In the next slides, you can see some information about genetic programming, how it works, and some applications of genetic programming, and also why we use genetic programming in our problem. Genetic programming is a type of evolutionary algorithm, as we seen in our previous slides, that evolves program to solve or approximate solution to problems. It also inspired from biological evaluation. The elements of genetic programming. Populations of programs. GP starts with a population of randomly generated computer programs. These programs are typically represented as tree structures, with nodes representing functions and leaves representing input data or constants. The selection, fitness function, and genetic operators are work similarly to evolutionary algorithms, what we discussed earlier. Now let's move to next slide. Evolutionary process. The process of selection, reproduction, and mutation is repeated over many generations. Over time, the population of programs evolves, with successive generation typically becoming more effective at solving the problems. GPs have been applied in various fields, including symbolic regression, automated theorem, machine learning, automated programming, and evolving control systems for robots and industrial processes. The advantages of GPs are flexibility and automatic program generation. GP is highly adaptable and can be applied to a wide range of problems. It can automatically generate programs without human intervention, which is particularly useful in domains where the solution is not obvious. And the challenges the GP faces are: it can be computationally intensive and may require a large number of generations to find the effective solution. Why genetic programming? Because of its evolutionary nature, creative problem solving, flexibility, and adaptability. And the evolutionary nature of GP allows it to explore various solutions simultaneously, improving over generations. This can lead to more robust models that are well adapted to the given data. GP can sometimes come up with a creative solution that might not be immediately obvious to human programmers. Thank you. The rest of the part will be explained by Ananya.